In this video, I'll be describing and illustrating the various parameters available for designing or modeling a chamber in UniformityPro. First, I'll introduce the chamber maps, which allows us to quickly see what is being modeled. This XY chamber map shows a projection on the chamber floor of the planet, parts, sources, and masks. And this shows a profile of the same. Sources are shown as large circles, which you can see here and down here. I can change the color of my source by going up here to the Sources panel and choosing a new color. This larger object is a representation of the planet in a double rotation configuration. We can also see this as a faint dark line here on this 30 line. This smaller object is a part that we're modeling. I can change its color here on the Parts panel, and we'll make it red. If we need to add multiple sources or multiple parts, the colors really help differentiate and clarify the various objects. This small green circle on this part is a specific point on the selected part in this parts drop-down. That point is changed from these X and Y inputs, and as I change it on one panel, you can see that it changes it on the other panel down here. And these values are in the coordinate system of the part. Now, the default focus for both of these chamber maps is the chamber middle. And what I mean by that is what is centered and will prove as our focal point as we zoom in and out. Now that's done with this minimum plot width. Right now it's set to 35. So that's saying that of the two axes, whichever one is the shorter one will be 35 units in length. So since this axis here is the shorter one, as I scroll on this, you can see that it starts to essentially zoom out. And then I can go the other way to zoom in. And so this isn't affecting anything to do with uniformity, it's just changing our view in the chamber map. You can see that they're also independent. Here this one didn't move, but I can change it. Now you can see my red part there. But oftentimes you'll want to look at something else. So you can click this down arrow here, and we have this option Plot Focus. And let's choose the part point. Now as I zoom in, you'll see that that point that I specified earlier is where we're zooming into. And I'll do that here as well, zoom in. I'll change it up here to part point, and there's our part. So if I made this a negative 0.5, we'd see both of them shift, and so this green point is still the center of this chamber map. This green dashed line coming from the point on our part shows the part normal at this point. So I'll go down here to the Parts panel and I'll say that I want a curved part. So here on the surface figure flat, let me change it to spheric, and I'll make the radius of curvature 5. Now you can see that this point, normal, is going this direction, and as I move in the X direction, you can see that that normal is changing. And here I went off the part, and so they just both went red, and I can no longer, it doesn't know what to focus on. But as I find a point that's back on the part, it'll jump right back to it. This solid line is showing the line of sight from the source that we have selected to the point on our part. Now I'm going to zoom back out on this one and we'll choose chamber middle. And what I'll do is I'll say show path of one orbit. And so this is now that path of this point as it goes through the chamber. And I can move this, and this is essentially a representation of time as it goes through the first complete orbit of the planet. Now notice that here I'm showing the path of one orbit, but on this panel is where I determine the orbits for my run that I'd like to model. And they're completely independent. I could say that I want only model half of an orbit, but I can still show 1, 2, or more orbits here. And so just want to make sure that you don't confuse those two. And this also shows each moment that is being sampled as it gathers the information about the uniformity of the deposition. So I'll go back and make this one orbit, and I'll make this one orbit. And instead of 500, I'll just say 10. Now you can see that this is significantly thinned out. And so this is showing that there's going to be 10 moments or samples per revolution of the planet. And since our gear ratio is over 4, then we'll have at least 40 points here. I can double this, or double it again. You can see it's getting denser. The significance of the steps per revolution is it has a direct consequence on the accuracy and speed of the uniformity calculation. If I put 80 steps per revolution, that calculation will take twice as long as 40. And when designing masks, we'll want this to be especially dense so that we can get a good idea of where that mask edge is, and so that it models that correctly. We found that it's most effective to leave orbits and steps per revolution relatively small at the beginning. This keeps the calculation fast and allows you to make quick changes. But as you get further through the process, increase the steps per revolution to ensure very fine accuracy. There's one more chamber map located up here, the 3D chamber map. And down here it has a special button because it takes a little bit longer to render these 3D maps. So we have to click it. And there it is. Now once it's rendered, I can move about this 3D space. The controls are, if I hold down the right mouse button and move my mouse, now I'm rotating about that point that's highlighted there, which happens to be the center of the chamber and also where our source is located. I can use the mouse wheel to zoom in and out of that point. And then I can hold down the left mouse button to change where that focal point is. So let's say that I wanted to zoom into my part here. There we go. Now I'm looking at a fairly close-up perspective of the part. You can also see each of those sample points. This object here helps you see your orientation in the chamber. As I rotate there, front, left, right, back, top and bottom, up or down. And if I click on one of these faces, it'll just jump so that it's straight on in each of those views. But we can also do the same thing where we can choose the camera target, and let's choose the planet middle for this one. And so now it's automatically changed where that point is that I'm rotating about. Similar to how it worked in these other chamber maps. Now you'll see that many of these are duplicated controls, so that if you're only looking at one chamber map, then you'll always have them available. With the addition of the render button, which we've talked about, there's this auto update, which is turned off by default. When it's checked, the 3D chamber map will regenerate anytime a change is made. But again, that can be costly in the sense of how much time it takes to render that, especially depending on your processor. So if I turn this off, now as I make changes, this will stay the same. So for instance, I'll change the part to be in the center of my planet. You can see that these updated immediately, but this is still over here. I'd have to click this button, and now I'm matching this chamber map with these. The last thing to look at is this here. It's labeled as the chamber map point angle of incidence histogram for the full run. So that's saying that it's modeling however many orbits I've indicated here. At this point, this is a distribution of the AOI, specifically of the selected point of the specified part from the specified source. And so here we're seeing that slightly more than half of the angles of incidence throughout this run are somewhere between 20 and 30 degrees, and slightly less than half are between 10 and 20. And again, that's specific to this point. Now there is one more box that I forgot to mention, this Show Uniformity of Selected Source. So now by clicking on that, I'll render this, and it's overlaid the uniformity that we see from our uniformity plot. Now since this isn't very dense, it didn't translate very well. So I'll add a higher density to my part. Let's say 21 by 21. Now as I go back to my chamber map and I'll re-render, we're seeing the same colors as we do here. We can make this a little easier to see by altering the minimum of my color axis. Let's say 0.95, we'll go to 1.05, go 0.97 to 103. There we go. We can at least see a greater variety of color. As I go back and render that, there we go, now we can see that. And so again, that's overlaid on top of the part. And because my part is round, right now the UniformityPro has to model this as a rectangle, and so anything that's not a valid point on the part is shown in blue and just kind of at a default level, aligned with the plane of the planet. Now I'll turn this back off and re-render it, and now I'm left with just that wireframe. These points provide insight, especially when modeling masks. When I add a mask, if deposition does not occur at this point in time, that dot will not show up. So I'll quickly add a mask. And put it in range here. So now as I zoom in, I'll zoom in on my part. And I'll make this dense so we can see it. There you can see that this green line is being interrupted by that mask. Also notice that it's not going to the edge of the mask, and that's due to the parallax. As you can see here, my mask is down a bit from the part. And now that we have even more variety of color, I'll go back and remodel that chamber map. There, and now indeed there's the mask. And And so as you go through here, you can gain insight into what's contributing to the non-uniformity. I'll turn these off again and turn off this mask. Delete it. I'll return to low resolution. And this panel, Chamber Geometry, helps show at a glance what the different chamber parameters do. We've got big R, which is the distance from the chamber center line to the center of the planet. That's located here. I've got H, which is the distance from the chamber floor to the center of the planet, or rather, the distance from the chamber floor to the height of the center of the planet. And that's given here. Alpha 0 is the beginning angle in degrees of the orbiting of the center of the planet. So if it were 0, the center of the planet would start right here on the positive x-axis. But in this image, it's probably about 30 or so. And beta 0 is the beginning angle in degrees of the planet rotation. So let's look at a few of these. I'm going to make this blue again so it's a little easier to see. And turn this off. Now I'm going to make my part the same size as my planet. Put it back to being flat. And so now as I track along with this point, I'm essentially tracking along this planet. So let's put this out at 5 and 0. Again, here's how that will be moving. So let's say that we want to start at 45 degrees or 90. Notice that the orientation of the planet is still at this point being to the right of the center of the planet. And as I alter planet beta 0, now I'm rotating the planet in place. And for now, I'll actually go ahead and hide my part so we can focus more on the planet. This little checkbox I can check, or uncheck rather, and now I'm just looking at my planet here. The number of lines to define the planet is given right here with the number of longitude and latitude lines. So these are purely for just plotting purposes. And they're especially helpful when having a non-flat planet, which I can do here under Planet Surface Figure. Let's make it spheric. I have these other choices as well. And we'll say the radius of curvature is 30. So now in this case I might want to see a higher definition. I'll change this to 6 or 8. Now we can see more here. The little r here is the planet radius. And then right above it we've got the planet tilt. So I could tilt this at 45 degrees, say. And let me put that part back on. So now you can see it traveling up and down because of the tilt. Established there. I'll turn that back off. And I'll set that back to 3. Now, gear method, we have two options, ratio or cogs. If the gear ratio is not known, then you can enter in the number of sun and planet cogs. You can see now I've got that as an option. These will always be integers. Go back to ratio. The number of planet rotations per orbit will be the gear ratio plus 1. So when the gear ratio is 0, there's no planet spin. Which we can see here. It's orbiting, but it's remaining fixed. It's not spinning itself. So it appears to rotate once, but that's due to its orbit. So if I say gear ratio is 1, then it'll actually go around twice. There's once right there. You can see that my point is now on the right side. And then we'll go a second one. So gear ratio plus 1. Counter rotate, when it's unchecked, then the planet rotation or spin is counterclockwise looking down. And we've been seeing that here. When it's checked, now the planet rotation is clockwise looking down. And so now you can see that this point, instead of going around that way, is staying towards the center of the chamber, at least at first. Notice that the planet's center orbit is counterclockwise for either option. All this is determining is the rotation of the planet. It's also important to note that counter-rotation, these two things involve entirely different gear structures. As we look at the path, in fact, I can make this a little more complicated there. You can see that's the shape with the counter-rotate. Versus the counterclockwise rotation. Finally, angle factor is the power of the cosine of the angle of arrival on the part. And normally we just leave this equal to 1. There's one last thing we need to look at on this panel, and that's planet rotation type. We were using double rotation. As I switch it to single, you'll notice that a lot of those options went away, and now we have a new chamber geometry map. H is now the distance from the chamber floor to the center of the dome. R, little r, is now the distance from the chamber center line to the edge of the dome. And alpha 0, again, is the beginning angle in degrees now of the dome rotation. As with double rotation, we have the following options for the surface figure: flat, spheric, conic, or conic aspheric. And as I choose each one, we'll see different options come up. Flat doesn't have any. Spheric, there's the radius of curvature. Conic, we have the conic coefficient. And now with the added aspheres. Next, we'll move on to the parts panel, which I've placed down here. UniformityPro allows for an unlimited number of parts to be modeled simultaneously, and parts may be of any shape and of any figure. As with the sources and masks panels, the parts panel at the top has this bar of options: color, the thickness of the plot, a title or name, and then the edit button. So right now my part is red. Let's make it kind of this magenta, and I can make that edge thicker. See, it's getting bolder there. I can turn that part off and on. And right now that's the only part that I have, but I'll click here and I'll rename it and I'll call it part 1. While I'm here, I can either click on this, or I can right click on here and I get the same menu, or I can go up to the parts menu and say add new part, delete the part, or duplicate it. I can also export parts to a file so that I could import them later into a separate UniformityPro configuration file. This is also true with masks, chamber, and sources. But now I'll go back and duplicate that part. I'll say add new. And so now I've got a new part here. You can see it added it right there. And now I have two. These are automatically sorted alphabetically. I'll call this one part 2. And we'll make this part this dark shade of green. Now as I come up to this drop down, notice that the checkbox is colored magenta here and green here, corresponding with the color we've assigned to it. And I can turn parts on and off right from this menu right here. Or if I have a part selected, I can check that box right from here without opening up that drop down. That'll turn it on or off. So for now I'll disable part 1 and we can look at part 2. Let's zoom in on this a bit. The radial position is the distance from the planet center or the dome center to the part center. So you can see here we're 6 units out. And angle position refers to the angle of the part center with respect to the x-axis. So I can make this 45 and now we've got it up there. Now I'll put a tilt on this part. If you have a curved dome or a curved planet, Auto will allow you to put in a specific tilt angle and then it'll place it at the correct radial position. But since I'm calling my dome flat, I'll switch to manual. And now I could enter in 45 degrees and you can see it tilted there. I'll change the dome surface figure to spheric and you can see it's kept my tilt there at 45 degrees. It's also added this sag line. The sag is the vertical distance from the plane of the tip of the dome to the part center. So now I'll choose Auto and see it kept the sag in the radial position and it updated my tilt. Let me change this to 30 degrees. Now we can see that it's moved to where a part tilted at 30 degrees would be tangent to the surface of the dome. And I can move each of these, and the others, as I move tilt, sag and radial position will change. If I change sag, radial position and tilt will change. And as I move radial position, sag and tilt will change. So those three are interconnected. Next, let's look at the curvature mount and mount offset properties. Vertex refers to that the vertex of the curved part is at the planet's surface, or in the case of a flat part, that the part center is at the planet's surface. If I look at the profile, and I'll zoom in on the center of my part, this faint gray line is my dome edge, and here's my part, and you can see it's at this point meeting the planet's surface. The other option is to choose edge mounting, and now you can see that the position at the radius of the part is now at the planet's surface. This also means that the vertex could be higher or lower than the planet, depending upon the sign of the curvature. To model a recessed part, there's the mount offset option, which is the distance between the tangent plane. So if I make this 0.5, I've raised it up 0.5 and we go down 0.5. Now it came down this way by half of a unit. Next, under the surface figure option, we can choose from flat, spheric, conic, conic aspheric, toric, toric aspheric, and even a custom figure which enables user-specified sag values and which can be accessed through this Customize button. So I'll choose that and say Custom, and now that opened up a window, Customize Part Shape and Surface Figure. So listed here is my part at these equally spaced intervals, and here I have access to the diameter and the X and Y resolution. This is referring to the number of sample points that's used in the uniformity plot. Now that may or may not be the number of sample points in each direction that's used to calculate uniformity. That's used over here on the targets panel. I've got this match part resolution checkbox. If that's checked, then when I change the X or Y resolution, that'll change it here so that they're interlocked. But if I uncheck that, I could be looking at on my uniformity plot at a totally different density of sample points than is actually being calculated with the merit function. So for example, let's say that you had custom sag values for this circular part that could be pasted into this 11 by 11 grid. But when optimizing, maybe you only need 5 by 5 to get good uniformity, and that'll save you time. I have some sag values on the clipboard, which I'll now paste into this data grid. Because I have a circular part, I can't click on these cells, but I can click here. That selects everything, and then I can either right click and say paste, or just use the keyboard shortcut Control V. You can see now I have these sag values pasted in. So I'll say OK. And you can see that those values are modeled. I can go to the 3D chamber map. And let's put the focus as the part center. And you can see that this is essentially a torque part, but I've manually entered in those sag values. Now that I have those entered in, I could measure uniformity at any arbitrary part on this surface. And if it doesn't fall on one of these grid points that we've entered in, the sag value will be interpolated. Now going back to customize, I could make that a rectangle. And now you can see these other values have become available. When I clicked that, there are also a few other values that were generated along the edge. They were actually there before, but just hidden. And that's to help with modeling edge values. When you have a custom surface figure and a set shape, that process is automatic. And you can see down here there's this button, Generate Edge Values. And that's grayed out. But I could also have a custom shape. And now I have checkboxes corresponding with each sag value. And this is where I can define my part shape. Now I have a few options down here. That's just blank to get us started, or full rectangle would be everything. An ellipse, lemniscate, like an infinity symbol there, or matching the starting shape. That'll just recreate whatever you came in with. So I'm going to go back to ellipse, and I'm going to take out this corner. And I'll make these 0 values, because they're not really valid anymore. In fact, I'll just paste in those values that I had to get rid of those generated edge values. Oh, well, it looks like I had values for a whole square part. Well, I'll make these 0 here, cut out this corner. Similar to Excel, there's this little box here that I can grab and bring down to fill a column. If I double click it, it'll fill the whole column. And I can even establish a pattern, and it'll continue that. Just a way of doing quick data entry. Now I'll uncheck all of these zeros that I just put in. I could have left all those values in that I had pasted, but I want to show what generate edge values does when you have a custom shape. So go ahead and click this, and it filled in these points right here. So even though my part doesn't extend that far, it uses these values to more accurately model what we've declared as the edge of our part. I'll click OK. Let's look at my part now. There we can see that corner cut out of it now. Now we'll go back to Customize, and we'll go back to Flat, and instead of Custom we'll make it a rectangle. Now as I choose these different options, you can see that it takes out those points on the part on its own. And right here, since this is no longer a custom surface figure, these are generated sag values. I can't edit them, so if I change it to spheric, you can see there that those are generated and I can't change them. I'll make it -2. You can see now those all went positive. Instead of a circle, let's do an ellipse. Now instead of diameter, I have a separate X and a Y width. And I'll click OK, and let's see how that looks. Good. You can see those values that I updated are now reflected in the parts panel. Let's actually go back and make it a circle. And instead of being vertex mounted, let's make it edge mounted. Now you can see that dropped into place there. And I'll zoom out again. Let's put a part on a different row. So I'm going to get rid of part 1. I don't really want it anymore. So I'll go to Parts and say Delete. Deleting this part will change the normalization part. Continue. Let's say yes, and I'll talk about in a second what that means. We'll take part 2 and let's duplicate part 2. And so now I can just change the radial position, 6, maybe a little more, 7. And now I've got a second row with an identical part. And I'll call this one row 2. And I'll call this one row 1. And I'll change the color of this one to be red. I'll update my 3D chamber map. You can see here that at this point, at this part, my histogram shows that everything for this run will be between 20 and 30 degrees. But if I switch to row 2, now everything's coming out of the green part and the AOI went up to 40 degrees. So again, that's just illustrating that this is all in respect to the selected part in this drop-down. Now I'll go back to the uniformity plot, and you can see I have 2 plots. Row 1 for my only source, untitled source, and row 2. Again, there's my red part and my green part. We can see that outline. These are pretty tight bounds for the axis. I'll make it 0.8 to 1.2. Let's see if that was enough. No, I'm still saturating. Let's go to 0.5 to 1.5. I like to have it with this blue, white, red palette so that one is halfway between these two. And that way uniformity will be white, and easy to see that if it shifts to red then it's a little thick and blue will be a little thin. I'm going to get rid of these contour lines as well. Now here I've got normalization part and X and Y. Uniformity is dimensionless, and it's calculated by the accumulated thickness divided by the thickness at a specified normalization point. So perfect uniformity would show 1s all across the part. There can only be one normalization point regardless of the number of parts, and so this is where we can specify that. So I'm saying that on my row 1 part at the center, that is going to be 1. And I just held down the left mouse button to get that. And sure enough, value is 1. Now let me shift this to x equals 0.5. Everything shifted blue because I chose a thicker part to be my normalization point. And it's actually not on this plot, so I don't see it, which is okay, but I'll make it 0.4 so I can show that normalization point there. Now instead of being on row 2, I'll switch it to row, excuse me, instead of being on row 1, I'll switch it to row 2, which didn't shift it that much because they're about the same in that place, but now that's 1, and that's going to be a little off from 1. In this report, I see that there's my normalization point thickness with my RMS, peak to valley, and my merit function. Right now I'm looking at my active parts. I could say that I just want to see row 1. And so now I can concentrate on row 1 and appreciate this bigger plot. Or likewise just row 2. Or I could see both. Let me add another source. And now I've got 4. I'm showing both parts and both sources, and those are labeled there. And again, if I want, I can see just from one source or another. So I'll go ahead and delete this source that I just added. And under plot here, I've got a few different options. Uniformity, I can see the angle of incidence for the full run at each of these points. And these are thickness weighted. I can also see the current chamber map position, and I'm going to make this a double rotation. And now as I go around, you'll see those plots update in real time there. Showing what the angle of incidence would be at that chamber map position. Now back here a little ways, we see this point is crossed over into red and has gone beyond that so that we have gray. You can see it's not a number. So that implies that at this point the angle of incidence was above 90 and this could not deposit anything. I can also see uniformity and the full run angle of incidence side by side. This target drop-down is explained in the video on sources and has particular value when fitting a plume. The final thing here is this check for self-shadow. It's off by default because it requires twice the amount of time to do that check. And so if you can anticipate in your run that there will not be a self-shadow issue, I would leave it off. But if that is indeed something that you need to account for, then definitely check that. I'll note that it will not check if one part blocks deposition onto another part. This is merely just one part with itself. So let's show what that would look like. I'm going to turn that off and make row 1 in the center of my planet. And I'm going to match my dome curvature. And since I'm not using this part anymore, I want to keep it loaded, but I just don't want to be looking at it. So here's where I can look at just row 1. Oh, it's because of this. I'll turn on uniformity, and I'll just look at my active part. Oh yes, which is row 1. Okay, good. So this is implying that it's all not getting any deposition at all. In fact, my merit function is not a number. My normalization point thickness is not a number. Let's see if we can see why. Let's go a little further out. Well, I can see that I'm getting deposition because I'm getting blue points on that show path of one orbit. And if there was no deposition, these wouldn't appear when that's checked. But here, my normalization part I left as row 2. And since I turned it off, it doesn't have a normalization point thickness to reference, so I need to switch that back to row 1. There we go. I'll put it back to the center of the part. Now let's drop this dome down a bit and look at a point over here. Not a bad angle of incidence. You can see that difference between the normal and the line of sight. But if my source were to the left, or my part came out further, let's change that. Now this is intersecting right there. I'm going to change this to be the planet middle and zoom in. So this is a case of self-shadowing. But I'm not doing that check, and so it won't apply. But if I check for self-shadow, I'll turn that on. You can see my merit function change became not a number because my normalization point thickness is 0, suggesting that at the center of the part it's not getting any deposition. Sure enough, I don't have that blue circle anymore. And right here I have an X on the part at the point that is causing self-shadow to occur. Now I'm going to restore it back to what I had, so let's get rid of row 1 part. Yes. I'll turn that back on and I'll duplicate that one again. I liked that part. And we'll go back to a single rotation dome. When doing single rotation, you only need to do 1 orbit if you're going to perform an integer number of orbits. By leaving it at 1, you'll save quite a bit of calculation time. If you do find yourself having long calculations, you can uncheck Auto Plot, which is similar to the Auto Plot button on the 3D chamber map panel. This just means that when I make changes, it won't immediately calculate that. I'll have to manually say update plot. For now I'll leave it on. So here I have a case where my targets line up with my resolution density. But I'll turn off part resolution, match part resolution. So my targets is 161. I'm going to drop that down to 5 by 5. So this is still 11 by 11, but my number of targets has significantly gone down. And notably that was just on row 2. If I want to change row 1, I'd have to select it and modify it as well. I'll keep it back to row 2. These are those target values, suggesting that we're targeting perfect uniformity. Now if I wanted to, I could go to targets and say target value. And these are the actual targets that I'm looking at. I'll make them bigger here. Notice that this one is missing. That's because it's the normalization point, so it will always be 1. I can also see the modeled value, which is the value at each of these points. I can even turn off this show surface plot to hide that grid behind, so if I only just want to focus on my targets. This is probably most useful, again, when dealing with fitting plumes, but also when having arbitrarily spaced targets. As an example, I have some targets on the clipboard, so I'll go Uniformity, Surface, Arbitrary Spacing. I'll add a target to get started. Let's see here, I want to be on, row 2. I'll paste it in here. I just, let's see, I don't have targets for row 1, so I'll turn those off. Now, since I'm targeting uniformity, I know that all these are going to be white. So instead of seeing the target value, let me see the model value. And now I'm only looking at these specific points, but I want them a little bigger. And so here's a case where showing the whole surface plot isn't as necessary, because I can focus on just the points that I want to see, and I'd still be able to watch these colors change as the merit function goes down. There's one final feature on the Targets panel that I'd like to explain. If I'm working with a uniformly spaced set of targets, let's say for example that I have a square part, and as it fits, I'd like to see the uniformity across the whole part, but I'm really only concerned with the central section of it. In that case, I can go down to this target shape where it says same as part. I need to be on row 1. And I'm going to say circle. Now you can see that there's this circle that's been added, and I can change its size. And as I change it, notice that the number of targets changes. From 20 and then its original 80 with a 2-inch diameter. If I turn it off completely, I get all 120. So that's a really nice quick way of just eliminating these edges that you don't, or rather aren't concerned with. That concludes this tutorial. Don't hesitate to let us know if you have any other questions.